Hello everyone, you are welcome to the seminar of deep learning and applications. In this seminar we will study different algorithms of deep learning and also their applications. And before we start those algorithms, we need first to introduce the major concepts of mathematics needed to understand the algorithms, mainly deep learning and actually in general machine learning in general. Algorithms are standing on two main pillars. They are linear algebra and probability and stochastic process. So those two main pillars to understand the algorithms of machine learning, and deep learning is the same. So we will start with linear algebra in these sessions. However, since we have students with non-technical background, so we will start with the very basic things. However, of course, during the course we will need to accelerate the speed of introducing concepts in order to be able to finish in a proper time. So we cannot spend very long time to talk about basic things. However, that I will start today with very basic concepts here. In the first session, I will divide this linear algebra into several parts. So now we are part 1.1, which means that part 1 is linear algebra, and this is the session 1 in linear algebra. So it is part 1.1. We might have about maybe up to 10 of these sessions in linear algebra before we start the session of probability and stochastic process. Okay, so let us go for the main things here. Okay, let me activate the pen. Pen color is white, yes. I will use the interactive method in the explanation, so I don't have pre-prepared material. So just we talk together about some few concepts here. We can explain them more in the online session. If you have questions, please write them down and you can ask me in the online session. As I said, I will start with very basic things. So I will start with the scalar. So what is the scalar? Scalar is a number on the number line or line of numbers, where we can put, for example, the origin point 0, and then we have here positive numbers, and in this side the negative numbers. For example, if we assume that x equal to 5, it means that we have 5 here to the right direction of the 0, and we will have minus 5 to the left direction. However, you can see here that any operation that we are doing is over this line. So we have, if we talk about face, so actually we have only two faces here that can be defined over the real numbers. So we can here define only in one dimension. You can see that this is one dimensional now. So we have only 0 degree, which means that it is on the right side of the 0 of the origin, and we have 180 degree, which means that on the left side of the origin point. So 5, we can say that 5 is 5 with angle 0, and minus 5 is also actually 5 but with angle 180 degree. Okay, so this is the concepts here. So we can of course multiply numbers here. We have many operations can be done over these real numbers. So this is called scalar. So this is the scalar that we have. Okay, now if we want to represent number in 2 dimensions, let's say that we have x and y. Okay, since now we have 2 dimensions, then we need to represent them into like vector. So if we have vector v equal to, let's say it is x1 and y1, okay, then it is now 2-dimensional representation. So v is 2-dimensional, not scalar. Scalar is 1 dimension. Now v is 2 dimension, where it means that we have x1 in the x direction and we have, for example, y1 in y direction. Okay, what is the difference now between one dimension and two dimensions. Actually, now with two dimensions we can represent this v with different, like it has also magnitude and phase, and now it can be any phase. It can be from 0 up to 360 degree, so you can rotate actually the whole points here. So for example, now with this x1 and y1, if we made just points like this and y like this, and this is the vector v. Now vector v, it represents a magnitude v, and also it has phi theta. So this vector now, it has magnitude, and it has phase. So it should be represented by two things, magnitude and phase. Okay, what is the magnitude of this v? Of course, it is easy to find. The magnitude is x, because this is x, it will be x1 squared plus y1 squared and the square root. So the magnitude of v is square root of x1 squared plus y1 squared. This is the magnitude. What is the phase? We know that the tangent of the angle theta is equal to the opposite is y1 divided by the adjacent x1. Okay, so this is the tangent of the phi or theta, sorry. So in that case, the angle theta equal to tan inverse of y1 divided by x1. So now we can represent this vector, which contains now two numbers, into like y1, like magnitude and phase, like which is like magnitude of v and angle theta of tan inverse y1 divided by x1. Usually we call this is like first square, the second square, and the third square, and the fourth square. So this theta actually, it can rotate. This theta, it can rotate, as we can see. So now if we go to the next, we take a new slide to show more. Okay, so now let us go back to the same angle that to the same figure. Yes. Yeah, so now we have this is x and y. Okay, and now we have like x1 and y1 again. Okay, so and we have the magnitude is the magnitude value of v, and we have, as we said, that x1 y1, this is the vector. Now this is the vector v. Okay, remember here that now in two dimensions configuration we have two like orthogonal axes or bases. We have x axis and y axis. Both of them, they are perpendicular to each other or orthogonal to each other. So the shadow of y on x is equal to 0. So they are in orthogonal, like orthogonal or perpendicular to x. Okay, and now any point in these two dimensions, any point here, any point could be represented with x and y. For example, we can have another vector v is at, let's say, 5 and 2. We might have like, this is v1, v2. We might have another v like -1 and -3, and so on. So any point here could be represented with two numbers or vectors with two dimensions. So you can now represent any point in these two dimensions, and every point it might have it is on magnitude and it is on phase. So you can, for example, this one, it has different magnitude and has different phase, and so on. Okay, and now if you rotate this line, if we rotate this line, let us call this is r. Okay, if we rotate r, then we will have circle. We will have circle in these two dimensions. Okay, and now what is the length of this r on x-axis and on y-axis? To find the length of r, or the projection of r on x-axis, always you take the phase, the cosine of phase between x-axis and r. So the distance here, the projection of r on x-axis, if we call it like x, okay, let us call it xi for example, or xr, is equal to r cosine theta, and this is theta. Okay, what is the projection of x on y-axis? It is yr equal to r sine theta. So remember this. So the projection of r on x-axis, you take the cosine of the angle between the axis or the line r and x-axis. So you just take the cosine, it will give you the projection of r over x. And if you take the sine, sinusoid, or the sine of this theta, then it will give you the projection on the other axis, which is perpendicular to x-axis. So this is the way that we can find them, and you can again at any time you can calculate r, because actually if you take x r square plus y r square, this equal to r square cosine square theta plus r square sine square theta, and you can take r square as a common factor. This gives you cosine square theta plus sine square theta, and this is equal to 1, so that r square equal to xr square plus yr square, and then r equal to square root of xr square plus yr square, as we have seen before. Okay, now if this line is moving with certain angular speed, okay, with certain angular speed, then we can also calculate how this will be changing, because this x, for example, if theta is equal to 0, then the same r will be also the same length of x1, but after that it will increase, the projection will decrease until reach 0, okay, and then it will increase in the other side, and then it will also go to 0, and so on. So this will give you the cosine wave. Actually, this gives you the cosine wave. This is the reason that cosine wave, the cosine signal, for example, cosine omega t or sine omega t, actually they are generated from the fact that we have some particle or some point moving in circular direction, or similar to circular. Okay, so that will generate the movements in x and movements in y will follow cosine and sine sinusoidal signal. Okay, so this is when we talk about two dimensions. So in 2 dimension, when we talk about vector, remember this, vector means that we have direction and we have magnitude. We have magnitude and we have direction. But when we talk about a scalar, then mainly we have only magnitude, or and we have only two directions to compared with the origin point. But in 2 dimension, we can have any direction of the parameter or the factor v. Okay, and actually this could be also generalized to any length. For example, let us go to the new slide, y1 and z1. So in this case, we talk about 3 dimensions. So we have the x-axis, and we have, for example, here we can have we can keep the same, so it is y-axis, and we can have here, for example, z-axis. Of course, this is just it is not possible, of course, to have 3 real axes on 2 dimensions as we draw them. But now you can imagine that this z is going out from the screen. Okay, now we have 3 dimensions as the space that we live in. So we have 3 dimensions, x and y and z. So here we might have a point at certain z1, for example, at certain z1, and we have a point at x1, Okay, this is x1, and also at y1, so we might have a point. So now, okay, sorry for this. We might have a point, this point, for example. So it can be also represented like certain y1 and x1 and z1. So now we have this point. Okay, so this point is in three dimensions. So we have now vector in three dimensions, xy, x1, y1, and z1. So and now you can see that we have face also theta with x, for example, and we have also another phi signal with y, because now we have two like two dimensional that above each other. So we have now these two dimensions here, and now we have another dimensions up them. So in this case we have a three-dimensional vector. So this is the three-dimensional vector. Remember here that x and y and z, all of them, they are perpendicular to each other. X and y and z, all of them, they are perpendicular to each other. And then we assume that we have the point, the original point 0, and once we determine at some reference point as like 0 point, then any point in the space could be represented by this vector. Any point can be represented by this vector. So now we have a vector with three elements. We can have also any number actually of dimensions, but it will be more theoretical. In this case, it cannot be even imagined that we have that, for example, v with like many dimensions, like we have maybe we have x1, x2, x3, x4 up to x8, for example. Then now we have 8 dimensions. Of course, you cannot imagine those in space. You cannot project those in space, in real space, but we can use them. They have a lot of applications where we need to have perpendicular like spaces. It can be for any n in numbers. Even sometimes we can have infinity number of perpendicular spaces, as we are doing usually when we have this like Fourier series, for example. We can have infinity number of perpendicular spaces. Of course, the spaces could be fixed or static, and it can be also time varying spaces. So this x, for example, this x can be like static, or it can be also function in time. Okay, and when they are function in time, they can move. Actually, they can rotate, they can move. However, that we should preserve all the time the perpendicularity between every paces. So all paces are all the time, they are perpendicular to each other, but all of them, they can change with time in any trajectory. But still we can have that this orthogonality concept should be also always like preserve it or reserve it during the movement of the axes together. Okay, this is actually, now we talk about the general in vectors. There's one thing more before we end this session, is the transpose. We can make the transpose of vectors. For example, when we have vector v, then we have, this is called column vector, x1, y1, z1. But if you take the transpose of this vector, then we will have row vector. It will be x1, y1, z1. That's all. Okay, so the transpose is just converting every column vector to be a row vector. Okay, there is one thing also more, is the mathematical operations on vectors. Let us have like just revise them very fast. Okay, like operations that could be done over vectors. What kind of operations that we can perform over vectors? Assume in general that we have vector with like column vector v with n elements. So we have, let's say, v1, vector v1 with x1, x2 till xn. Okay, so if all these numbers, actually for each number in this vector, it can be a real number or it can be also complex number. Okay, so if they are real numbers, then we can say that v1 is like real numbers with vectors which is like n by 1. So this means that they are real numbers, okay, and they have n elements, and one, it means that it is like, we know that it is a column vector because it has n rows. You can see it has n rows, okay. And if they are complex numbers, then usually they are represented like v1 belongs to complex number c is n times 1 as well. Okay, so it can be real numbers, those elements, or it can be complex numbers. And as we explained before, now we are talking about n-dimensional space. We have n-dimensional space where each space is orthogonal to all other spaces. This is important to remember. Each space of those n, each one is orthogonal to the others or perpendicular to the others. As I said, we can have in the practice, we can, or on reality, on real life, or on real space, we have only 3 dimensions. But in mathematics, we can have any number of orthogonal spaces. Okay, and now how to multiply, or let us start how to add or subtract 2 vectors together. Remember that if you multiply this v1 with a scalar, for example, if we multiply, like we have now, let's say y equal to 5 times v1, this is the same as multiplying 5 in each of the elements. So it will be 5x1, 5x2 till 5xn. Okay, this is the way that how to multiply a scalar into a vector v1. Okay, how to add vectors together. So assume that we have like another vector v2, which is contains, for example, y1, y2 till yn, and it is also belongs to the same, it can be, of course, both of them, they can the same numbers, the same number type or type of numbers, or it can be different. It can be v2, it can be real numbers, can be also complex numbers, but it should be the same dimension. So it is also like for example r n by 1 or complex n by 1. Okay, now how can we add those vectors together? Then, for example, assume that we have scalar number alpha 1 times v1 plus alpha 2 times v2. Okay, simply it will be, the result will be alpha 1 times each of those elements, so it will be alpha 1 x1, okay, plus alpha 2, it will be multiplied in each of these elements, so it will be plus alpha 2 y1. Okay, and this will be alpha 1 x2 plus alpha 2 y2, and so on until alpha 1 xn plus alpha 2 yn. Okay, as you can see here, what is the main condition to be able to add 2 vectors? They must have the same size. They must have the same size. You cannot, for example, if I ask you to add like 5 2 1 plus 2 3, this is invalid operation in general. Of course, we are not now talking about basic concepts. Of course, there are some things that you can insert some 0 here, for example, to be able to make this operation valid. But now it is not possible to add these 2 vectors together. Okay, so this is important to remember. And now how to multiply vectors together? Okay, to multiply vectors together, the number, it should be in this way. So for example, if we have v1 as it is here, now it is n by 1, and v2, which is also like n by 1. So now it is not possible to multiply them together. It is not possible to multiply as a matrix multiplication. I am talking about matrix or vector multiplication. It is not possible to multiply them when they are in this size. So if we have, for example, x1, x2 until xn multiplied by like y1, y2 till yn, what we need here, it is not possible to multiply them in vector multiplication in this way. Okay, the legal way to multiply vectors as to have like the number of column in the first vector must be the same as the number of rows in the second vector. Okay, for example, this one is n by 1 and this one is also n by 1. Now in the legal multiplication, of course there are some special kind of multiplication where you can multiply like element by element, but this we will come to it later. Now I am talking about basic operations of or the basic vector operations. Okay, and there is another way that it is called also canonical product. We have different kind of products in vectors and in matrices, but now let us start with the basic thing. So now it is not possible to multiply this one. Why? Because the number of how many columns that we have here, we have only one column, and how many rows we have here, we have only we have n rows. Okay, so to make the legal operation, and this is valid for vectors and also for matrices, that the number, okay, of columns of the first matrix or the first vector must be the same as the number of rows in the second vector or in the second matrix. So now this is not possible to multiply them with the basic multiplication. What can we do? For example, if you take the transpose of this vector, it will be possible, because when you take the transpose of this vector, it will be v1 transpose. Actually, now the dimensions becomes like, if it is a real number, it becomes like 1 times n. Okay, now it becomes 1 times n, and here we have n times 1, so it is possible. So now v1 transpose times v2, it is like the dimension of 1 times n, and the dimension here is n times 1, so it is possible to make the multiplication, and the result will be 1 times 1, which means that it will be a scalar. Okay, how to make this operation? It is easy. So we have x1 x2 till xn multiplied by y1 y2 till yn. Okay, now this multiplication will result as x1 times y1, it will be x1 times y1 plus x2 times y2 plus x3 times y3 until plus xn times yn. So actually this vector, it is also known as the dot products between vectors. So the result will be summation of xi yi from I equal to 1 till n. So this is called the vector dot product between vectors. What if we swap it? So what happened if we make like a swap instead that we make like v1 times v2 transpose? What happened? What happened if we make v1 times v2 transpose? This what we are showing now. Let us go to a new slide. Okay, so yes, so now if we multiply v1, now v1 is x1 x2 till xn, and we want to multiply it with y1 y2 till yn. Now it is v1 times v2 transpose. Now if you look to the dimension of v1 is real numbers or complex, of course, and the dimension is n by 1. As you can see, we have n rows. The first number always is the number of rows, the second is the number of columns, and multiplied by, and now the second one, because we take the transpose, so it becomes like 1 times times n. So we have only one row, but we have n columns. Okay, so the result, because those are the same number, and now the condition or the required condition for multiplication of vectors and matrices has been achieved, that we have the number of rows the number of columns in the first vector is the same as the number of rows in the second vector, then the result will be n by n matrix. So when we multiply these two vectors together, then the result will be like that. So x1, you take the first row times the first column, but here the first row contains only one element and the first column contains one element, so it will be x1 times y1, and then x1 times y2, x1 times y3, and we continue until x1 times yn, and then x2 times y1, so x2 times y2, and continue until x2 times yn. And then we can continue in this way until we reach to the last element is xn times yn. Of course, here we have xn times y1, and so on. So now we have a new matrix. This is the result of the multiplication of two vectors. When the first vector is column and the second vector is row, then we will have matrix in this way, and this matrix is n by n. Okay, so this is important to remember. Okay, now is it possible to multiply if we have two vectors but not the same n? So maybe this one is n by 1 and this one is 1 by m. Yes, it is possible, and the result will be a matrix with dimension n by m. Let us take a numerical example to explain this concept. Okay, now assume that we have two vectors, x equal to a vector like 5, 2, 3, okay, and x equal to another vector but with only two elements, so it is 7 and 1. Okay, now we want to multiply those two vectors. Okay, now what is the dimension of this? The first y, the dimension is real numbers, and it has three rows by one column, and x is also real numbers, but it has 2 rows times 1 column. Okay, now it is clear that we cannot add xy plus xy plus x is not allowed. Okay, also y times x is not allowed. Those are wrong. Those are wrong operation or illegal operation in the basic vector analysis. Okay, but we can see that if it is possible to multiply like y multiply x transpose. Okay, what will happen now? Y multiplied x transpose, it means that now we have real numbers 3 times 1, and x transpose is real numbers but now is 1 times 2. Okay, yes, it is possible because now the condition has been achieved. Okay, as you can see that the number of columns in the first one is the same as the number of rows in the second one, which means that we will have, it is possible to make this operation and we will have a matrix with dimension of 3 times 2. Let us do it together. So we have here 5, 2, 3 times, when we make the transpose here, it will be 7, 1. Okay, and the result will be 5 times 7 is 35, 5 times 1 is 5, 2 times 7 is 14, 2 times 1 is 2, 3 times 7 is 21, 3 times 1 is 3. Okay, now this is the result of this multiplication, of this dot product or multiplication of these two vectors, where we have, here we have a dimension of 3 times 1, and here we have dimension of 3 times 2, and now the dimension is 3 rows, 1, 2, 3, and 2 vectors, 1, 2, so it is 3 times 2. Okay, so now if I asked you, make this the same, but I want you to generate a matrix with a dimension of 2 times 3, is that possible? Yes, it is possible that, and you can now make it in, you can swap them, so we can have instead of y times x transpose, because now we you want to get 2 times 3, so it can be x times y transpose. X times y transpose, then x is now the dimension is 2 times 1, and now y, the dimension is 1 times 3 because it is transpose here, so the result will be 2 times 3. Let us see how it will generate, or what it will generate. So it is 7 1 times like 5 2 3. So the result will be 7 times 5 is 35, 7 times 2 is 14, 7 times 3 is 21, 1 times 5 is 5, 1 times 2 is 2, and 1 times 3 is 3. Okay, so you can see that we have 35 now, 14 and 21. Okay, and we have, so here yes, this would be 21, not 31 actually. Yes, 21, and then we have 5 2 and 3. So this now the dimension is 2 times 3. Okay, so this is now how to make the basic vector operation, and in the next session we will talk about matrices and what is the concept of matrix. Now we know the concept of vector. Vector is a point in space where the number of perpendicular, or the bases in that space, is the same as the number of the elements in that vector. Okay, and usually we talk about column vector, but of course row vector is the same concept as well. And now when we talk about matrix like this, what matrices means, what matrices mean. So we will talk later about what matrix mean, and then we will talk more, and we will go deeper in about analysis about when we talk about rank of a matrix, and then we talk about eigenvectors and eigenvalues, what is the physical meaning of those, and how to use them. But this is now the vector that we with like in elements. And just before I end this session, I forget to mention also what is tensor. Okay, what are tensors? Now we know vectors, what are vectors are clear, but what are tensors? Okay, so actually again I will summarize them. Scalar is a single number in one dimension, so we have one dimension. So a scalar, for example, x equal to 5 is a scalar. Okay, x equal to like 5 to 7, for example, is a vector. Okay, x equal to like let's say 1 2 3 0 1 0 and maybe minus 1 7 was 1 plus j, like complex number. This is called matrix. So the matrix now is like consists of several vectors together, and this matrix is usually we specify them with the number of rows times the number of vectors. So the number of rows is 3, number of vectors is 3, so we have 3 by 3 as we have seen. Now you can have any number of elements here. It can be in general like n times m or whatever. So you can have 5 by 7, you can have like 200 by 1 million, so you can have any number of elements in matrix. This is called matrix. Okay, now if we talk about a three-dimensional matrix, so if we have, let's say, not two-dimensional like this one, but we have like this is the matrix, okay, that we know. So we have matrix, but also we have another dimension of the same matrix, like this way. Okay, so we have another dimensions. So actually for every, now we have like blocks. Okay, you can see that we have not only 2 dimensions as it is here, but we have also a block. We have like a block like this one, and we have another second block, but behind this also we have another one, another block, and we have here another block, and so on. So now we might have like in the same way we have maybe n row by m vector, n row by m vector, but we have here also elements, let's say call them k. So we have n by m by k. Now this called tensor. This one is called tensor. For example, you have element here, for example here 3 7 5 4 and so on, but also we have here another number like for example -1 and so on. So now if you take only one element, if you take for example n by m, but for one slide, for example, let's say we take the third slide here, so this is a vector now, sorry, this is a matrix now. It is a matrix n by m because we specified the number here at 3. We specified it at 3, okay, when we specify certain number. So we take only one slide, but in general, when we say, for example, 5 by 4 by 4, for example, what it means that you have 4 matrices, and each matrix is 5 by 4 dimensions. So we have 5 by 4, and we have behind it 5 by 4, 5 by 4, and 5 by 4. This is called tensor. This together is called tensor. For example, if we have image, we have video, and each video is image, so the image itself is a matrix. The image, one image is a matrix, but this images are changing with time, so it moves with time. So we have like tensor. Tensor is very important in deep learning, as we will see when we deal with many images like in sequential to each other. So we need to deal with tensors as well. So now we have, remember, we have scalar, we have vector, we have matrix, and we have tensors. So this is now we end this part with this very general definition, with very basic starting, and what is coming is a little bit more advanced to be able to catch the main concepts of deep learning algorithms. Thank you very much for your watching. Thanks.